2,000 years ago, builders in Rome, Persia, and the Nubian desert engineered roofs that cooled homes for free. They dropped indoor temperatures by up to 12 degrees without electricity. Modern sensors confirm it. These designs used 85% less energy than anything we build today. Then, within a single century, we replaced all of it. The question is not whether these roofs worked. It is what made us stop using them. In the ruins of Pompeii, a single house stands out to researchers, the House of the Surgeon. Its roof, still largely intact after nearly 2,000 years, holds a secret that modern science has only recently confirmed. Archaeologist Dr. Maria Carus led a multi-year sensor campaign inside this Roman villa, placing temperature and humidity loggers both in the central atrium and within the vaulted roof cavity above. The data, collected during peak Mediterranean summers, revealed a striking pattern. While outdoor temperatures soared above 35 degrees Celsius, the rooms below the roof remained 5 to 7 degrees cooler. This was not a lucky accident of old masonry. The roof was built with interlocking clay tiles arranged over a shallow vault that created a deliberate air gap. During the hottest hours, the cavity acted as a buffer, absorbing heat and slowing its transfer to the living space below. At night, the same mass released stored heat back to the cool sky, smoothing out temperature swings and keeping the house comfortable through the next day's heat. Computational fluid dynamics models, based on three-dimensional laser scans of the original structure, show that this vaulted chamber was not just a static barrier. It encouraged natural convection, as warm air rose and exited through small vents, and cooler air was drawn up from the atrium, creating a gentle, continuous flow. Dr. Carus describes the House of the Surgeon's roof as a climate control device, engineered centuries before the first air conditioner. The measured interior temperature reduction, consistently 5 to 7 degrees below ambient, matches what today's building scientists call a thermal lag. The design did not just shelter, it actively managed the Roman summer, proving that ancient builders understood and harnessed the physics of passive cooling. In the heart of Iran's Yazd province, a different ancient approach to passive cooling rises above the skyline. The Badjir, or wind catcher. These tall, slender towers are more than architectural ornaments. They are precision-engineered devices for harnessing the desert wind. Professor Ali Rezai, a building science researcher at the University of Tehran, has spent years measuring what happens inside these shafts. His team's field instruments recorded average airflow speeds of 1.2 meters per second inside a typical Badjir during the hottest summer afternoons. That's a steady, invisible wind channeling through the living spaces below, even when the air outside is still. The process begins when prevailing breezes strike the tower's open face. Air is funneled down a vertical shaft, where it passes along thick mud brick walls. These walls, made from locally sourced silt and straw, have a thermal conductivity of 0.35 watts per meter. Kelvin, about half that of modern concrete. As the air travels downward, the bricks absorb some of its heat, cooling it further before it enters the home. Temperature sensors inside Yazd's historic houses show that when the Badjir is active, indoor temperatures can drop by as much as 12 degrees Celsius compared to the outdoor peak. Residents describe a rush of cool, dry air sweeping through courtyards and bedrooms, making the house feel comfortable even as the desert sun blazes outside. Professor Rezai notes that the Badjir's effectiveness does not rely on electricity or moving parts, only the physics of pressure, temperature, and carefully chosen materials. This system transforms the harsh, dry wind into a silent, reliable source of comfort, illustrating another way ancient architecture worked with nature, not against it. In the villages along the Nile's edge, the Nubian vault rises from the desert floor, a gentle curve of earth bricks assembled without timber or metal, sheltering families from the relentless Saharan sun. Unlike Roman and Persian strategies, this roof leans on sheer mass and the slow, patient movement of heat. During the hottest hours, thick walls, sometimes 30 centimeters deep, absorb solar energy, their surfaces remaining 4 to 6 degrees cooler than the air outside. Infrared thermography conducted by the Egyptian Ministry of Antiquities between 2020 and 2023 paints a vivid picture. The vault's interior glows blue on the hottest afternoons, while neighboring concrete roofs blaze red. But the real secret comes after sunset. As the desert cools, the vault slowly releases the heat it stored, creating a gentle, comforting warmth inside, while the outside air turns cold and dry. Descendants of Nubian builders interviewed in 2022 recall sleeping soundly under these domes. One elder describes how, on moonlit nights, the air inside felt almost fresh, even when the sand outside still radiated the day's heat. The vault's geometry, arched and unbroken, funnels warm air upward where it escapes through a small vent, drawing cooler air from shaded courtyards below. Over generations, this cycle became part of daily life, woven into memory and routine. When Egyptian architect Hassan Fathi revived the Nubian vault in the mid-20th century, he drew on both tradition and observation. His sketches, preserved in the archives, show how the vault's curvature and mass moderate the wild swings of desert temperature, smoothing extremes into a steady comfort. Scientific surveys confirm what local families have always known. These roofs, built from earth and sky, deliver comfort without a single watt of electricity. The evidence, sensor data, thermal images, and lived experience completes a triangle of passive cooling strategies, each rooted in place, each guided by the same physics. Ancient builders, separated by continents and centuries, converged on 4 principles that still anchor passive cooling: airflow, thermal mass, shading, and material choice. Each principle stands up to modern laboratory scrutiny, revealing the science behind enduring comfort. AR flow comes first. In climate chamber experiments, researchers built scale models of Roman vaults, Persian wind catchers, and Nubian earth roofs. Smoke tracers and hot disk sensors mapped air currents as even small temperature differences sparked convection. The Roman roof's 15-centimeter cavity sent warm air rising at nearly 0.8 meters per second, echoing Pompeii's ancient homes. The Persian badger, crafted from mud brick, funneled air at 1.2 meters per second, enough to refresh a room's air every 30 minutes. The Nubian vault, using the stack effect, created a gentle upward draft after sunset as thick earthen walls release stored heat. Thermal mass forms the second pillar. Hot disk tests showed Roman tiles, dense at 2,200 kilograms per cubic meter, absorbed enough heat to delay indoor temperature peaks by hours. Nubian earth bricks, lighter but with greater specific heat, steadied interior temperatures through the hottest afternoons. Shading and surface reflectance quietly shape comfort. Lab tests of lime, washed and whitewashed surfaces found high albedo finishes, reflected up to 70% of sunlight, cutting solar heat gain by a third. Roof shapes, arched, vaulted, or with deep eaves, cast shadows that shielded living spaces below. Material choice completes the system. Hygroscopic clay and earth absorbed and released moisture, keeping humidity stable even as outside air dried out. Comfort simulations using the predicted mean vote index, known as PMV, delivered a score of plus 0.5, slightly warm but within the comfort zone, without mechanical cooling. Compared to flat concrete roofs with air conditioning, these ancient designs cut energy use by over 85%. The numbers speak for themselves. The same physics that cooled homes 2,000 years ago still work today. By the early 20th century, a new set of actors stepped onto the stage: manufacturers, marketers, and code writers, each with their own vision of comfort. In 1906, Carrier Corporation introduced its first commercial air conditioning unit with a bold promise: control the climate, control the comfort. That phrase, repeated in trade journals and glossy advertisements, framed mechanical cooling not as a tool for survival, but as a symbol of progress. Hospitals, theaters, and luxury homes became the first adopters, their status amplified by the hum of compressors hidden behind walls. The message landed. By the 1950s, real estate ads in suburban America featured central air as a luxury upgrade, pushing property values higher, sometimes by as much as 12%. Insurance guidelines began to penalize homes without mechanical systems, citing fire risk from open windows and older cooling devices. Meanwhile, television sitcoms made the thermostat a fixture of modern life, a subtle marker of arrival into the post-war middle class. But it was not just marketing that tipped the scales. In 1973, the Uniform Building Code introduced language that fundamentally changed how architects and developers approached comfort. New buildings, especially commercial ones, were required to meet minimum ventilation rates that passive systems could not always guarantee. By 1975, code clauses made mechanical heating, ventilation, and air conditioning mandatory for most new construction. The logic was simple. With denser cities and sealed glass towers, passive roofs alone were no longer considered sufficient to manage heat and air quality. Institutional momentum took over. Developers, facing pressure from insurers and code officials, defaulted to mechanical systems. Architects, trained on new standards, left the old roof designs behind. The physics of thermal mass, stack effect, and shading, once the backbone of comfort, gave way to the hum of compressors and the promise of year-round climate control at the flick of a switch. The passive roof, proven by centuries of lived experience and hard data, was sidelined not by failure, but by a new definition of progress written into law and culture. Today, buildings account for nearly 40% of global energy use, much of it for cooling. As heat waves intensify, rediscovering passive roof designs is not nostalgia, it is urgent adaptation. The knowledge never vanished. The real question is whether we have the will to build with nature again. What do you think?